So it's 11 o'clock. Let us start. So very warm good morning to all of you. Welcome in next lecture of Math F242 Operation Research. So last time we have discussed about the basics of simulation. Let us understand the simulation through the example. So this is a solved example from your book. In a queuing system with single server, assume that customers arrive such that each customer is 2 minutes. So here inter-arrival time is given to you 2 minutes. It is a fixed. It is a deterministic model. And the service time for each customer is 3.5 minutes. I trust audio video is okay.
Yes, sir.
Service time for each customer is 3.5 minutes. It is also fixed. Simulate the system using next event increment method for 15 minutes. So you have to simulate the process of queuing, process of arrival departure, right, for the 15 minutes. If inter-arrival time is fixed 2 minutes and service time is also fixed by 3.5 minutes. So here we have the table. So when we will see the table at the starting, we assume the first customer arrive. Right here we have the event. So means this is the time. So at that zero time, first customer will arrive, then only you can give the service. So in the third column, we have total number of arrivals so far. So at the zero, we have the total number of arrival 1, total number of departure so far. So there is no departure. So it will be the 0. Then total number of customer in the system. So here we have the total number of customer in the system will be the 1. In the queue is 0. And since clock just started, so waiting time in system, waiting time in queue will be the 0. Now inter-arrival time is fixed by 2 minutes. So next customer will come at the 2 minute. No service we have given. So in system now we have the two customers and one customer in service, one customer in queue. So this customer, right? This customer will wait up to the time 2. So will wait for the 2 minutes. So total time will become the right. It is the total time spent in the system between the preceding and the present instant. So the first customer arrive at 0 time and he has to wait up to the 2 unit of time. So total time will become the 2 unit. And here number of customer in queue, that is the 0. So 0 customer has to wait, uh, right? Because there is no customer, so no waiting time in queue. Then after, next customer will come at the 4. Next customer will come at the 4. But before that, the customer who has joined at 0 unit of time, he will depart from the system at the time 3.5. At the time 3.5. So at this time we have the departure event. So because there is a departure, arrival number of arrival will remain same. This is the first departure, so 1. So due to the departure, number of customer in queue will decrease. So now it remain only 1, and in queue there is a 0. Now these two customer will wait for the time difference 3.5 and 2. Time difference between the 3.5 and 2. So total waiting time will become right? Here we have the 1.5 unit, 1.5 unit of time for the two customers. So total time will become the 3 unit of time. And one customer in queue, one customer in queue also wait for the time difference between 3.5 and 2. So total will be the 1.5. So here we have the 1.5. So time is spent in queue. Then at the 4, we have the arrival. So this is the third arrival. Till now we have only the one departure. So number of customer will increase by 1. So now it will become the 2 customer, and number of customer in queue, one in service, one in queue. And this one customer will wait for the 4 minus 3.5 unit of time, and this 0 customer will wait for the time, right? 4 minus 3.5 unit of time. So time spent in system will become zero point 0.5, and in the queue it will become the 0. So the next customer will come at the 6, next customer will depart at the 7, right? Then next customer will arrive at the 8, then next at the 10 will depart at the 10.5, and at the 14 there is the arrival and departure simultaneously. Just here I'm demonstrating how to make the table. I have written here A and D simultaneously, but I have already told you never we will assume arrival and departure occurs simultaneously. So when I will show you the correct table, right, means table in detail, at that time I will write the A and D separately. Just here to explain, at the 14 we have the both things, arrival and departure. I have written simultaneously. At the 15 we have to end. So at the 15 we have to end. So whatever the, there is no arrival, no departure, so all the data will remain as it is. Only the what will happen, this four customer, these four customer will wait for the difference between 15 and 4, 15 and 14. So here we have the 4 minute, and these three customer in queue will wait for 15 minus 14 unit of time. So it will become the 3. So in this way we can simulate the table or arrival and departure process for the system. So from here we can estimate the average waiting time in the system. So W will become, it is the total waiting time in the system 39, and for how many customers, that is the 8. Means if you take the sum of these, so this will come the 39, and here total number of arrival till now we have the 8. So expected waiting time, estimated value of the expected waiting time will become the CWTS upon CNA. This is the CWTS upon CNA. Means cumulative waiting time in system divided by the cumulative number of arrival. So it will become 39 upon 8 or 4.875. So on an average, each customer has to wait so much time. Average waiting time in the queue, so that is the WQ. So WQ we write as a CWTQ, cumulative waiting time in the queue, upon CNA. CNA means total number of cumulative number of arrival. So total waiting time, here it will come, if you take the sum, so this will come as a 24. So this will come 24, and CNA is the 8. CNA is 8. So it will become 24 by 8. So on an average, 3 unit of time customer has to wait in the queue. Average number of customer in the system, that is the L. So L we compute as a CWTS, cumulative waiting time in system, divide by the Tmax. Tmax, and LQ will become the CWTQ upon Tmax. Tmax is given to you, maximum time is given to you as a 15 unit of time. This is the CWTS, this is the CWTQ. So when we divide, so you will get the estimated value of the, so it is the estimated value of the W, WQ, L and LQ, whatever the whatever the performance measure for the queuing system. So here we have seen we have the deterministic model, but in the real life, just I am demonstrating here how we should observe the different activity or event, right, for the process. So right, a random number usually taken the deterministic model, but always we cannot take the deterministic model. So some problem are you facing?
Yes, sir, there are a lot of breaks in your voice.
Sarthak Gupta, just wait a bit. I'm changing the
Yes,
net.
sir.
So now hopefully it will be corrected. Still, if you feel any problem, then you tell me. So I have demonstrated you how to take the observation for the event, right, in any process. Now, if these events are random, so for including the randomness, we have to include the distribution, and for including the randomness, we take the help of the random number. So what is the random number? Random number we generally generate by the computer program, or we have the random number table. So what is the characteristic of the random number? Random number has the characteristic that it never repeat. Whatever the infinite number of random number you require, you can use. Never the sequence of the numbers repeat. That is the characteristic of the random number, and it is uniformly distributed. Means all the digits have the equal probability, right? All digits have the equal probability. So random number, the digit from 0 to 9 are arranged in such a manner that while choosing all digits are equally likely. Thus the PDF for the for choosing, for selecting any digit will be the 1 by 10. 1 by 10. So when we are choosing a single digit, similarly when we have to choose a 3 digit, 4 digit random number, at that time total we have the number, means like what, it range from the 00, 001, 002, 010, and so on. Then we have the 100, then we have the 999. So how many numbers we have here? Here we have the 1000 number. Here we have the 1000 number. So fx for this will become the 1 upon 1000. Means each 3-digit numbers are equally likely and having the probability 1 by 1000. Common mistake generally we have seen in the exam from the student side, that when we have the number 000, so student simply write that it is the 0. It is correct. It is wrong. Means when we are saying 3-digit random number, so you have to write the 3-digit. Means you cannot write 001 as a 1. You cannot write 010 as a 10. This is the wrong. When I'm saying that 3-digit number, so you have to write the 3 digits. Right? You cannot say that it is the same thing. So one can also use 3-digit random number or 4-digit random number, where say 3-digit random number are 000, 001 to 999, and all has the equal probability. So probability will be the 1 by 1000. So from here we can say that random number in general we denote by the u. Why we are denoting by the u? We say that random number u follow the uniform distribution between the 0 and 1. So 0 inclusive, 1 exclusive. Right? 0 between 0 and 1, 0 inclusive and 1 exclusive. Now, so as I have told you, for the with the help of the random number, we can generate any kind of the distribution, whether the discrete or continuous. So let us start that first. I will show you the distribution, how we can how we can generate the different kind of the distribution. Right, thereafter I will take the real time example. So first, generating the discrete random variable. So generating discrete random variable means here what we have. Let us say, um, let us say x is what? It is the discrete random variable. Discrete random variable means here. Let us say we have the x1, x2, x3, x4, and xn. So corresponding probability we know, means this is the x, and probability of x is equal to xi. So this will become the p1, p2, p3, p4, and pn. So you know that for the discrete, sum of pi is equal to 1 I from 1 to n. So if you have to generate the discrete variable or the discrete distribution, so what we have to do? First, we have to compute the CDF. So what is the CDF? What is the CDF? CDF is the x less than equal to xi. So for here we have the P1. For here we have the P1 plus P2. For here we have the P1 plus P2 plus P3. For here we have the P1 plus P2 plus P3 plus P4. And for here we have the summation of Pi. I vary from the 1 to n. So what we will do? We develop the scheme. So we have to develop the scheme. So what is the scheme? That if x can take the value x1 if the random number is less than p1. It is the x2 if the random number lie between the p1 plus p2 less than uh, p1 less than p1 plus p2. x3 when u lie between the p1 plus p2, u less than P1 plus P2 plus P3. Similarly, X4 P1 plus P2 plus P3 U P1 plus P2 plus P3 plus P4. Similarly, Xn will become summation n is equal to I is equal to 1 to n minus 1 pi less than u less than summation I from 1 to n of pi. So with this scheme, you can generate different values of the x. So in this way, for the discrete distribution, we can generate right the discrete random variate, right? So same here it is written for the discrete distribution. Let us have the probability of x is equal to xi is equal to pi. So summation of pi is equal to 1. So here we have the scheme x will take the value x naught when u is less than p naught. We have taken the p1. Similarly, it takes the value xj if the u lie between the summation of pi up to j minus 1 and summation of pi up to the j. Most important thing to note here, always we are taking the is equal to on the left inequality. Always we are taking the is equal to on the left inequality. Right inequality, always we take the less than only, strictly less than. Right, so this is the scheme we have already discussed. Let us take one example. Let x be the discrete random variable with following distribution. X can take the value 1 2 3 4 0 0.2 0.1 0.4 0.3. So here we have x takes the value 1 2 3 4, and probability of x is equal to x is given to you as a, it is given to you as a 0.1 0.2 0.1 0.4 0.3. So it is given to you as a point 0.2 point 1 0.4 0.3. So from here, if you compute the probability x less than equal to x, so it will become the point 0.2 0.3 0.7 and 1. So range will come if you take the three two digit random number. So 0 0 2 1 9 2 0 2 2 9 3 0 2 6 9 and 7 0 2 9 9. So it is what whatever we have written in the same fashion we have written here. So this is the range or scheme. Now they have given the random number, u is given to you. U is given to you as a 0 0.9 0 0.1 0 0.1 0.6. So if the u is equal to, if you if u is equal to, we have the 0.9. So 0.9 lie between which interval? 0.9 lie between which interval? 0.9 lie between this interval, right? So here the x is equal to 4. Similarly, for the point 1 lie between means point 1 means 1 0. So point 1 lie between this range. So here the x is equal to 1. So in this way, we can write all the values of the x. So here we have the 4 corresponding to 0.9. It is 1 corresponding to 0.1. It is 1 corresponding to 0.1. It is 3 corresponding to 0.6. It is 2 corresponding to 0.2. right? So here then it is 3 corresponding to point 4, it is 3 corresponding to point 6, it is 4 corresponding to point 9, and it is 3 corresponding to point 5, and it is 4 corresponding to point 7. So you have generated the values of the x artificially, which follow which follow the this distribution, which follow this distribution. So that is the generation of different random variables or variates. So this is the general discrete distribution. Let us move to how we can generate the standard distribution. So you have the idea of the standard distribution like Bernoulli distribution, Bernoulli binomial, and Poisson. So let us understand how we can generate the Bernoulli random variate. So what you know about the Bernoulli random variate? Anyone, please give the idea.
Sir, it has only two outcomes.
Yes, very good. First thing is this.
P is probability that the event
We
takes
have the
the.
two, right? X. So it takes the two values, either the 0 or 1. So 0 we denote, right? 0 we denote the failure, and 1 we denote by the, right? It denote the failure, and 1 we denote as a success. The Bernoulli variate has the only the two outcomes, either the 0 or 1, which represent the failure or success. So can you tell what is the probability mass function or probability density function or point probability function for the Bernoulli variate? And if it is a success with probability small p, right? Bernoulli random variate with parameter p, you can say we are generating the Bernoulli variate with parameter p. So what is the p denote? It denotes the probability of the success in each Bernoulli trial. In each Bernoulli trial, whatever the probability of the success, we denote that by the small p. So when we take the p and it take the value 0, so its value, because here it is a failure with probability 1 minus p, that is the q. So it will become the 1 minus p, and probability of x is equal to 1, that is the success is the p. So if you write this as a this as above 1, it means what we are writing.
P of x equal to p power x times
Or
1.
if you want to write the, yes, if you want to write in terms of the fx, so it will become 1 minus p to power 1 minus x, right? 1 minus x into p to power x, where x can take the value 0 and 1. So when it is the 0, x is equal to 0, so probability will come the 1 minus p. When x is equal to 1, then the probability will come the p. So it is exactly the same whatever the we have here, we have here. So if you write in the tabular form, so here we have the x, right? X can take the value 0 and 1. Here we have the probability of x is equal to x, so it will become the 1 minus p, and it will become the p. So if you have to compute the CDF x less than equal to x, so here we have the 1 minus p, and here we have the 1. So it means if you want to write the scheme, so scheme will become, it is the either the 0 or 1. It is either the 0 or 1. When it is 0, when the uniformly distributed number, random number, u is less than 1 minus p, and when it is equal to 1, when u is greater than 1 minus p but less than 1, then we say x is equal to 1. So So in this way, we can generate the Bernoulli variate. So here we denote the failure by 0 and success by the 1, and probability of the success or success occur with probability small p. So here we can write the fx when x is equal to 0, it is 1 minus p. When x is equal to 1, it is p. Otherwise, it is 0. So we can write where p is the probability of success. So it lies between 0 and 1. 0 and 1. So how we can generate the Bernoulli random variate? So we know that px is what? Px is the p to power x 1 minus p to power 1 minus x, and x can take the value 0 and 1. So when x is equal to 0, when x is equal to 0, it will become the p to power 0 1 minus p to power 1 minus 0, that will give you 1 minus p. When x is equal to 1, so it will give you p to power 1 1 minus p to power 1 minus 1, so it will give you p. So from here, you will get the CDF as a 0 when x is less than 0, 1 minus p when x is less than where x is greater than 0 but less than 1, and it is equal to 1 when x greater than equal to 1. So from here we can develop the scheme x is equal to 0 if u is less than 1 minus p, and it is equal to 1 if u is greater than equal to 1 minus p, where x is the desired value of the x. Means x is what? X is it which follow the Bernoulli distribution, which follow the Bernoulli distribution, right? Bernoulli distribution. So in this way we can generate the Bernoulli random variate using the random number 0.678. Generate the observation of Bernoulli random variable x with p is equal to 0.4. So it is given to you x follow Bernoulli with p is equal to zero point 0.4. So what I have given you the scheme, x will take the value 0 when u is less than 1 minus p, and it takes the value 1 when u is greater than 1 minus p, greater than equal to 1 minus p. P is what? P is the 0.4. So 1 minus p will become the 0.6. So this will become, means this is the 0.6, this is the 0.6, and given number is what? 0.678. So 0.678 is more than the 0.6. So generated number will be the x is equal to 1. Generated number will be 1. So in this way we can generate the Bernoulli variate. So 1 minus p is equal to 0.6. U is given to you as a 0.678. So u is greater than 0.6. That is the x is equal to 1. So this is the generated value of the random Bernoulli random variate. Now next is the how we can generate the binomial distribution or binomial random variate. So binomial random for the binomial random variate, you know very important characteristic. For generating the binomial random variate, we know the very important characteristic. First, what is the x in the binomial distribution? What is the x? From that you will get the idea. What is the x?
Number of success in
Number of
n trials.
success. Number of success in n
Bernoulli trials.
Bernoulli trials. In n Bernoulli trials. So it can take any value 0 success, 1 success, 2 success, or at most n successes. So we know that point probability function or probability mass function for the binomial random variable will be the n comma p Bernoulli trial with probability p, you can say. So here x means we are assuming that x follow the binomial distribution with parameter n comma p, where n is what, number of Bernoulli trial, and p is the probability of success in each trial. So fxp, we know that it is what, it is the ncx p to power x 1 minus p to power n minus x, where x vary from 0 1 to n. Now, beside this, you know one more characteristic. Means here we have the Bernoulli trial, either the success failure, second Bernoulli trial success failure, third Bernoulli trial success failure, right? Similarly, we have the n Bernoulli trial success failure. We can have the any result. So x denote number of successes. So what is the result of the x1? What is the result of the x2? What is the result of the x3, whether the success or failure? What is the result of the xn? If you add this, it will give you total number of the successes, where x1 denote or xi denote, where where xi follow which distribution?
Bernoulli.
Bernoulli. Xi follow the Bernoulli distribution with parameter p. Means x is nothing, x is the sum of n independent Bernoulli variate. Bernoulli variate. X is nothing, it is the sum of n, right? Sum of n independent Bernoulli variate. And you know how to generate the Bernoulli variate from the last example you have seen. So just you take the you apply that approach, you will get the let us say here the x1 will come 1, x2 will come 0, x3 will come 1, x4 will come 0, x5 will come 0, right? X7 will come 0, x8 will come 1, x9 will come 0, x10 is coming 0. So it means x will become the 3. So in this way we can write the Bernoulli, or we can generate the Bernoulli binomial variate with the help of the Bernoulli variate. So let x be binomial random variable with parameter n comma p. Then x can be expressed as the sum of n independent Bernoulli random variable with parameter p, such that x is equal to x1 plus x2 plus xn, where xi's are independent Bernoulli random variable, each having parameter p. Hence, the value of the x of x can be generated by generating the value of xi I is equal to 1 to n. Then we write the x is equal to x1 plus x2 plus xn. The same thing we have done. So using a random number 0.775, 0.130, 0.382, 0.086, 0.864, 0.234, generate one observation of the binomial random variable with x, random variable x with n is equal to 6, p is equal to 0.4. So here it is given to you x follow the binomial distribution with parameter n is equal to 6 and p is equal to 0.4. So we know that 1 minus p will become the 0.6. So you know how to generate the Bernoulli variate. Let xi is equal to, it is the 0 or 1 when u is less than 1 minus p, that is the zero point 0.6. When u is greater than 1 minus p, that is the zero point 0.6. So xi can take the value 0 and 1. And here random numbers are given to you. Random numbers are given to you 775.775. So here the x1 will come the 1. Then random number is given to you. Random number is given to you as a 130382. So 130. So x2 will come 0. Then 382.382. So here x3 is equal to 0. Then we have 086864. 086, 086 and 864. So 086 will give you x4 is equal to 0 and this will give you x5 is equal to 1. And last number is 234. So 234.234. So here you will get the x6 is equal to 0. So what is the x? What is the x? X is the x1 plus x2 plus x6. So small x will become x1 plus x2 plus x6. So it will become the 1 plus 1. 1 plus 1. So it will become the 2. So using the 6 random numbers and with the help of the concept of means or relation between the binomial variate and Bernoulli variate, you can generate the binomial variate. So here we have the step means using this random number. So step 1 is what? X is equal to 0, right? And then after we compute the 1 minus p. If the random number is more than the 1 minus p, then xi is equal to 1. Otherwise xi is equal to 0. Now you can write, you can simulate the binomial variate by the table also. So from the table, if xi follow the binomial distribution with parameter n comma p, where n is what? 6 and p is given to you as a 0.4. So for this, if x is equal to 0, here we have the n is equal to 6 and p is equal to zero point 0.4. So for the x equal to 0, for the x equal to 1, for the x equal to 2, for the x is equal to 3, for the x equal to 4, for the x is equal to 5, and for the x equal to 6, we have the value of probability x less than equal to x. That is the CDF. So in every book you can have the table of the CDF. So when we have the table of the CDF, let's say it is the A, it is B, it is C, it is D, it is E, and it is 1. It is 1. Always the last will be the 1. So if the random number is less than A, right? If the random number is less than A, then x is equal to uh, 1 minute. A, B, C, D. Let's say it is the A, it is B, it is C, it is D, it is F, and it is F. So if x is less than A, then generated value of x will become the 0. If it is lie between A to B, then it is 1. If it is between B to C, then it is 2. And if it is between F to 1, it is the 6. It is the 6. So in this way, using standard table, you can generate easily the discrete variable. So here, using the random number 0.775, 0.382, 0.086, 0.864, 0.234 generate one observation of the binomial random variable x with n is equal to 6 and p is equal to 4. It's 0.4. So here it is wrongly written. It is not. It will give you the 6 observation. It will give you 6 observations. So from the table, we know f0 is equal to 0.067, f1 is equal to 0.233, f2 is equal to 0.5443, 0.8208, 0.9590, 0.9959, and at the 6 we have the 1. So you can see 775 lie between uh, this and this block, right? So here the f3 will become x will become the 3. I'm saying that what is the now range? Range will become the 0467, 0467 to the, or no, range will be the 0002 0466, 0466, 0467 0467 uh, 2332, 23332. It will give you 5442 and 54432. It will give you 8207, 82082, 9589. And here we have the 95902. This will give you 9958 and 99592, 9999. So 7750 will lie in this interval. So this is the corresponding to 0, this is corresponding to 1, 2, and this is corresponding to 3, this is corresponding to 4, and this is corresponding to 5, and this is corresponding to 6. So now the generated number will be the 3. 130, 130. So 130 will lie in this interval. So here we have the x is equal to 1. Then 382, 382 lie in this interval. So here we have the x is equal to 2. Similarly, 0886 lie in the first. So it will give you x is equal to 1. Right? So in this way, we can generate the binomial variate. So next is the generation of the continuous random variate. So we will start in next class. Time is almost over, so we will start this in next class. So is there any doubt?